Okay, well here, let's go on and talk about some quantum electron devices. These are going to be devices where the electrons transport is controlled by tunneling, okay? And hang on one moment. Okay, so we're going to talk about some tunneling devices. And, oops. Oh, excuse me. Let me draw this, I'll be right back. All right, tunneling devices. So first, of course, we remember that when an electron meets a barrier, that there's a probability of tunneling through. As we described in modern physics, okay? So if we make a graph of the tunneling probability, T, as a function of the energy of the carriers, we'll get something like this. So we know that the tunneling probability goes exponentially with the energy difference between the energy and the height of the energy barrier. But there's another phenomenon too that we didn't talk about in modern physics. Well, you'll see in just one moment. So as the energy increases, the tunneling rate increases. And like so. There's actually a maximum here, a resonance. So that the peak tunneling rate is actually a little bit closer to 1 than you would expect. This occurs because at the point where the electron energy exactly equals the energy of the barrier, there's no tunneling. There's also no reflection from the barrier. But at higher energies, electrons can still reflect from the barrier, even though the energy exceeds the energy of the barrier. So we get a resonance, particularly exactly at this point. Okay. All right. So now, if we imagine creating a device where we have two conducting layers separated by a barrier, we might expect to see an insulating barrier. We might expect to see tunneling between the two conducting layers, and we might be able to see this resonance as well. Okay. 1 second. Okay. This process and this resonance, they're the basis of something called an Esaki tunneling diode, which was developed in 1959 by Renoa Esaki. And he won the Nobel Prize for this in 1973. Esaki was a Japanese physicist. I think he might still be alive. And eventually a commercial device. Okay, and this is a tunneling process. I don't want to go into the details. It's a little complicated because we have electrons that tunnel from an N-type material to a P-type material in a p-n junction. But the idea is that we get this pattern in the tunneling rate, and it shows up in the current voltage characteristic of the device, because the current is proportional to the transmission probability, of course, and the energy of the electrons is proportional to their voltage. And what he showed is that there's a peak in the current, and then for higher voltages, the current actually decreases before it increases again. And this is kind of interesting because with something like this, where the current decreases as the voltage increases, you can make a kind of an oscillator, a very high frequency electronic oscillator. Anyway, that's application we don't need to talk about, but this is the Esaki diode. Now, even more beautiful and elegant is this double barrier structure. Okay? In the double barrier structure, there's a point where the tunneling probability can go to 1, and it's very sharply defined. In fact, it's the point at which the energy, well, imagine between these walls, you can have a confined state, because this is a quantum well, and we can have a confined, the electron confinement would lead to a energy state or a subband with a minimum energy, perhaps right here. And when the energy of the electrons that would tunnel through this barrier equals the energy of that confined state, then tunneling can be very efficient. David Bohm, a physicist who's famous for many things, did the first calculation of tunneling through a double barrier in 1951. And here it is. And what he showed is that there's this sharp resonance. And exactly at this energy, the double barrier structure becomes transparent. That is, the transmission goes to 1. But it's strongly cut down on either side of this magic resonance. And then at higher energy, there are second resonances, and then finally you can just get electrons to flow right over the top of the barrier. But this is the important part. Just to illustrate what's going on here, we can look at this. So here's the idea. We have this double barrier structure, and there's a confined energy state that exists between these two barriers. Okay, of course, at 0 voltage, no current can flow. And as we increase the voltage, we'll reach a point where electrons can efficiently tunnel into this energy state. Okay, and at this point, the transmission through this structure will be very high, so they can efficiently tunnel into the state, and then they can tunnel out and proceed along their merry way. If the voltage becomes larger, we'll move out of resonance. These two states will no longer align, and then the tunneling will be reduced, okay? Until finally we start to get current just flowing through the device because electrons can, well, because the voltage difference is so large. These different diagrams corresponding to these different points on this schematic current voltage graph. And once again, we see a peak, a particular voltage at which the current is maximum, and then after that it decreases, okay? The first experimental demonstration of a resonant tunneling diode was by Solner in the early 1980s, okay? Here's some recent data. Here's a double barrier structure. Here's an electron microscope image showing the two barriers here in our thin film structure. And then here's a current voltage characteristic for this device. You see a sharp peak, and the current drops rapidly on either side of the resonance peak. Okay, this work was done at the University of Cambridge. All right. So that's really interesting. So here's a kind of electronic device that only exists because of tunneling. And you can have, and so a device like this, first of all, it exhibits these unique characteristics. But you know, in a way, this is nice because the smaller you make the devices, the stronger and more apparent the quantum effects will be. So things like this, you might expect would work better and better as devices get smaller and smaller. Okay? Resonant tunneling diodes have not been used in commercial technology, to my knowledge. There might be some weird esoteric things I don't know about, I'm afraid. But and one of the issues is that systems like this are very susceptible to process variations. A small change in the thickness of one of these layers changes the tunneling rates a lot, and so it's hard to make, you know, a million resonant tunneling devices and have them all have exactly the same characteristics. But there is a tunneling device that's used that does have a very wide application. We'll talk about this a little bit later when we talk about magnetism. This is something called a magnetic tunnel junction, and it's the basis for essentially all hard disk drive readers now, okay? All right, I want to show you one more device before we quit. But before I do that, I really ought to just recognize the following. So we've talked about two areas where quantum wells are applied. They're applied in making more efficient light emitters. So they're applied in optoelectronics and for high-speed electronics. And in 2000, the Nobel Prize was awarded to Zores, Alferov, Herbert Kromer, and Jack Kilby. Jack Kilby was very important for the development of the integrated circuit, but Herb Kromer and Alferov developed heterostructures for optoelectronics and electronics applications. And one of my students, well, one of the, there's a McAllister student, Nelson Coates, who actually went and did his PhD with Herb Kromer in around 2005, and is now a professor out in California. So that's kind of fun. I want to talk about one more quantum device, and this is one that does have applications, although not very widespread. It's kind of a niche device, but it's really interesting. This is a quantum cascade laser. In a quantum cascade laser, electrons travel through a series of quantum wells by tunneling through the barriers between the quantum wells. And things are arranged in such a way that when the electrons tunnel from one well to the next, they tunnel resonantly into the upper state of the confined states in the quantum well. And then these states are engineered so that there's another state somewhat lower, and then a third state below that. And because the electrons are being pumped into the upper state in the heterostructure, they can emit light when they drop from the upper state to the intermediate state here. And in fact, you can develop a population inversion where you have more electrons in the upper state than in the intermediate state. And a population inversion is a necessary component for a laser. So it's a necessary component to have light amplification, because in that case, when light goes by, it can excite this transition. This transition produces more light at that frequency, and so you get gain. So this is a type of laser. You can see it's a laser that relies on inter-subband transitions, something that we talked about. And it works on the basis of quantum mechanical tunneling, where electrons tunnel from one quantum well into the next. Okay, these devices produce lasers that operate in the infrared part of the spectrum between, well, now they've been made to wavelengths out to 50 microns or so very long wavelengths to very short wavelengths, well, relatively short of 3 or 4 microns. So by changing the structure, you can make lasers that operate anywhere in the infrared part of the spectrum. And that's important because infrared lasers otherwise tend to be big, expensive gas laser systems like carbon dioxide lasers, whereas these are very small and compact. The other thing is that molecules have their signature vibrational absorption bands in the infrared. So you can use lasers like this to identify molecules in a gas, like molecules in the atmosphere, to make cheap and compact gas sensors for, say, carbon dioxide or methane or whatever else you'd like to detect. These were developed by Jerome Feist and Frederick Capasso and others at AT&T Bell Labs. I think at that point it was just Bell Labs, no more AT&T by 1996. And it was a pretty important discovery. It merited the cover of Science magazine. Anyway, I wanted to show you that. So now I think we'll stop and we'll see you in class.